In Chapter 3, Section 4, we want to look at the physical properties that are affected by the strength of the intermolecular forces. We'll start with boiling point. And here is the general trend. The stronger the intermolecular force, the higher the boiling point. So van der Waals compounds that only have van der Waals forces are going to have relatively low boiling points. Compounds that have dipole-dipole interactions will have somewhat higher boiling points. And compounds that have are capable of hydrogen bonding, they are going to have even higher boiling points. And here is an example or a series of examples here that demonstrate this. You need, in order to make this work, you need to pick compounds that have similar size, because if the size is different, then the strength of the van der Waals interactions are going to be substantially different. So you gotta keep them about the same size. So here we've got pentane, butanal, and butanol, butan-1-ol. And what we're going to find is, again, these are about the same size, but this one is only capable of the van der Waals interactions and has a boiling point of 36, which is relatively low. Butanal, with its dipole-dipole interactions, has a boiling point all the way up to 76, which is much higher. And then the butanol, with its OH there, has a boiling point of 118, and that is substantially higher. And there, of course, the hydrogen bonding is involved. All right, other factors that will affect boiling point are going to include surface area. If you have the same polar component, the same functional group, but you get a bigger molecule that has a larger surface area, then it is going to have stronger dispersion forces in addition to the dipole-dipole interaction, and that will cause it to have a higher boiling point. An example here, we've got 3-pentanone and acetone. The pentanone, the 3-pentanone here, has it does have the dipole-dipole interactions, but because it has these extra carbons, it also has extra van der Waals interactions. And so with that higher surface area, larger surface area, it has a higher boiling point. Polarizability, and we saw this in one of the ones we looked at on that last problem on number 24, part B. If we've got something that is more polarizable, in other words, a bigger atom that's further down on the periodic table, then that greater polarizability will increase the boiling point. So we'll find here that for iodomethane, it has a much higher boiling point than fluoromethane. And again, that fluoromethane, because that fluorine is not very polarizable. So let's look at numbers 27 and 28. We'll go over again to our in-class assignment. Look at 27 and 28. So here, rank the compounds in each group in order of increasing boiling point. So we want to see how they are different. Well, these are all alkyl iodides. So here we've got CH3, CH2,4I. This one has CH2,5I and CH2,6I. Since the only thing that's different is the size, we should expect the bigger ones to have stronger dispersion, or as we call them, the van der Waals interactions, and therefore they should have a higher boiling point. So it's actually going to be in this order. So CH3, CH2, 4, I is going to have a lower boiling point than CH3, CH2, 5. Yeah, I'm going to fix that real quick. I, which will have a lower boiling point than CH3, CH2, 6I. So again, this is just a difference in size. The longer that chain is, the higher the boiling point is going to be. On this one, we've got different types of interactions. So we've got CH3, CH2, CH2, NH2. All right, if we think about what kinds of interactions this is capable of, well, it definitely has van der Waals interactions. It also has polar bonds, so it has dipole-dipole. But this one, because of the hydrogens on the nitrogen, is capable of hydrogen bonding. Therefore, that has hydrogen bonding. This one doesn't have hydrogen on the nitrogen, so CH3, 3N, there's no hydrogen on the nitrogen. And so this one is just got dipole-dipole interaction. So that one should have a lower boiling point than this one. And then this one doesn't have any polar bonds at all. It's just got carbon and hydrogen, so it should have the lowest boiling point. So I'll put CH3, CH2, CH2, CH3 is less polar. It's not polar at all. And so it should have a lower boiling point than CH3, 3N, which has a lower boiling point than CH3, CH2, CH2, NH2. And again, this one dispersion only. This one has dipole-dipole, and this one is capable of hydrogen bonding. All right, next we want to look at this. So CH3, carbon, oxygen, carbon, CH3, 3. So that is an ether. And so it does have dipole-dipole. Let's look at this one. CH3, CH2, 3. All right, there's 3 of those. Oxygen, CH2, 3, CH3. So that's also an ether. So we'll have to distinguish between those here in just a moment. And then here we've got CH3, CH2, 7 OH. Well, clearly the one with the OH is going to have the highest boiling point because it's capable of hydrogen bonding. So we have to differentiate between these two. Well, the key difference here between these two, this one's going to be a much longer chain. It's going to have a greater surface area. And if you look, all 3 of these are actually isomers of each other, so they all have the same molecular formula. They just have different connectivity. So this one, again, this is one of those where it's already in the right order, but we'll go ahead and put it down here. So CH3, 3, C, O, C, CH3, 3. That one should have a lower boiling point than CH3, CH2, 3, oxygen, CH3, 2, CH3. And our highest boiling point should be that alcohol, CH3, CH2, 7 OH. All right, so next we've got 5 carbons here, so that's pentane. And then here we've got an alcohol, so this is, let's see, 1 pentanol. And here we've got one bromo, this is butanol. That's 1 butanol. This is 1 bromo butanol, or 1 bromo butane. And then this one is another alcohol. So we know the alcohols are going to have the highest. Our lowest are going to be these two. So we'll do 1, 2, 3, 4, 5. That'll be the lowest boiling point. And then 1, 2, 3, 4. Bromine, that'll be next. And then between these two alcohols, we know they're going to be highest because they have hydrogen bonding. Well, the longer one, the one with more carbons, should have a higher boiling point. So we'll put 1, 2, 3, 4 OH, and that should have a lower boiling point than 1, 2, 3, 4, 5 OH. All right, on this next one, it's all about shape. So what we're going to find is the longer, the more stretched out it is, and you'll see, again, these are all isomers of each other, but the more stretched out it is, the higher the boiling point is going to be. All right, so the one that's the least stretched out is this one. So 1, 2, 3, 4, 5, 6, 7. All right, so that one's the lowest. And then this one, 1, 2, 3, 4, 5, 6. And then we'll put a methyl there. So that one's going to have a higher boiling point than this one because it's a little bit more rod-shaped. And then the one that is completely linear should have the highest boiling point. So 1, 2, 3, 4, 5, 6, So that one should have the highest boiling point. All right, finally, here we've got 3 molecules that are about the same size, and we want to put these in order of increasing boiling point. We'll start with the one that's completely nonpolar. So that one should have the lowest boiling point. And then here we've got, this one's polar, but it has OH, so it has hydrogen bonding. This one should be polar because of those bonds, but it doesn't have the OH, so we will put it next. That one's called tetrahydrofuran, in case you're curious, or THF. It's a great solvent that we use. And then here, this last one, that should have the highest boiling point because of the hydrogen bonding. All right, so we want to explain why this one has a higher boiling point than this one. And I'm going to draw these out just real quick. So 1, 2, NH. There we go. So that's this one. And then this one is hydrogen, nitrogen, nitrogen. And then there are just 3 methyls that are attached to that nitrogen. Now, they both have lone pairs. We don't necessarily have to put those lone pairs in there, but they both have lone pair electrons on the nitrogen. The key difference, and they're both polar. So we've got polar bonds between carbon and nitrogen, and here we've got a polar bond between nitrogen and hydrogen. On this one, we just have the polar bonds between carbon and nitrogen. And since we don't have hydrogen, it's not capable of hydrogen bonding. So we will say that CH3, CH2, NHCH3 is capable of hydrogen bonding. Wow. CH3, 3N is not. And so since this one is capable of hydrogen bonding, it should have a higher boiling point. All right. Well, we're going to go back to our presentation. And so if we've got 2 things and we want to see which one has the higher boiling point, we can use a distillation apparatus, a distillation setup, kind of like this. And the way that it works is, again, this is just a method of separating compounds that have different boiling points. You put your components into a distillation pot or a distillation flask, and you start heating it up. And then the molecules that have a lower boiling point, more of those will get into the vapor phase than the molecules that have a higher boiling point. So they will go up the distillation column a little bit more easily than the ones that have the higher boiling point. And once they hit this bend, there's cool water that runs through this condenser. And so that substance will turn from a gas back into the liquid phase, and it will start dripping down. And so you'll get these drips of your liquid coming over. If you set it up really well, and there's this big enough difference in the boiling point, you can get almost pure, or sometimes practically pure, compound. It really just depends on how close those boiling points are. In addition to that, if your boiling points are close, then you can get a longer column. And then if you measure the temperature as the stuff's coming over, you can tell when it is you need to switch out the collection flask so that you can collect the other material. And this is just a handy way of separating things that have different boiling points. This is a fundamental organic chemistry lab skill, something that you need to know how to do. And so this is one that we do in the lab. All right, we want to take a real quick look at melting point trends. I don't have any in-class assignment questions on this, but melting point trends. We're going to find that as you increase the strength of the intermolecular forces, you generally will increase the melting point. But it's not as big of an impact as we saw with the boiling point. So definitely things with hydrogen bonding typically have higher boiling points than things that are just dipole-dipole or don't have any dipoles at all. However, when we look at these numbers, you'll see that they are not nearly as different as the numbers we saw when we were looking at boiling points. So here are our melting point for pentane, negative 130, and then for butanol, negative 96. So there is a pretty significant difference there because of the dipole. But then if we look with the hydrogen bonding, that hydrogen bonding is a lot stronger than just the regular dipole. But the the melting point only went up by 6 degrees. And so these are still pretty compressed as far as melting point goes. So definitely as you increase the strength of the interactions, melting points will go up. But we're going to find another factor here that turns out to be really important. And that is symmetry. And so compounds with the same functional group and similar molecular weights, the more symmetrical molecules tend to have a higher melting point. So we'll find that compact symmetrical molecules will pack into crystals much more efficiently and much more easily than asymmetric molecules. An example of this, a comparison here. Here again, these are isomers of each other, so they're our constitutional isomers. They're both C5H12. This one is 2-methylbutane. And you'll see that it's unsymmetrical, like this side isn't the same as this side. And, there's not as many planes of symmetry as you'll see in something like this, which is 2,2-dimethylpropane. And you'll see this one's much more ball-shaped. But this is a much more cylindrical, or not cylindrical, much more symmetrical molecule. And as a consequence, we will find that it has a higher melting point. So lower melting point for the less symmetrical molecule, and higher melting point for the more symmetrical molecule. And you'll see there's a very significant difference there in that melting point. All right, next we want to look at solubility trends. So solubility is just the extent to which a compound dissolves in a solvent. And what we're going to find is we need to look at the interactions that we get when we make a new solution and the interactions that we had to give up when we made that solution. So if we've got a compound, here is some compound like a solid, and there is the water, and we'll find, or not necessarily water, but the solvent, we'll find that in order to make a solution, we have to separate the solute particles apart from each other. And so we have to give up the solute-solute interactions that are occurring here. Now, when we do that, we're going to get new interactions between the solute particles and the solvent particles. So we will get new solute-solvent interactions. If these are about the same strength, the ones that you gave up and the ones that you got, they're about the same strength, then you're probably going to be able to make a solution. However, if these new interactions are much weaker than the old interactions that you gave up, then forming a solution is much less favorable. Now, it's not impossible because of the whole entropy thing, but it is definitely going to be more difficult to do. The rule that we like to use is it's just sort of a simple phrase, like dissolves like. So compounds that have similar polarities tend to dissolve each other. So compounds in solvents with similar types of intermolecular forces will dissolve other things with similar intermolecular forces. In other words, polar compounds tend to dissolve better in polar solvents, like water or alcohol. And nonpolar compounds, or weakly polar compounds, tend to dissolve better in nonpolar solvents like benzene or hexane or carbon tetrachloride, or something that's maybe weakly polar like diethyl ether. So it's still polar, but it's not as polar as water or alcohol. All right. So when it comes to ionic compounds, many ionic compounds will dissolve in water, but end up being insoluble in organic solvents. If you want to dissolve an ionic compound, then you need the very strong ion-ion interactions that you give up have to be compensated for with some ion dipole interactions. And so that's why we need a polar solvent to do this. And it helps if you get something that's even capable of hydrogen bonding. Those hydrogens really do help to solvate the ions. When it comes to organic molecules, how soluble they are depends really on how polar both the solute and the solvent are. So here, an organic compound is water soluble if it contains at least one polar functional group capable of hydrogen bonding with the solvent for every 5 carbons that are present in the compound. All right, so and we can compare the solubility of butane and acetone in water and carbon tetrachloride. So butane, nonpolar, when we put it into carbon tetrachloride, which is also nonpolar, it's soluble, so swimmingly soluble. So they're completely miscible. If you take miscible, by the way, miscible means 2 liquids are miscible if they can dissolve with each other in any ratio. So completely soluble is what we mean by that. Butane, if we put it into water, well, butane is nonpolar and water is polar. So the new interactions are only going to be dispersion forces, and they're not going to be as strong as the interactions that we get like between water molecules and between the butane molecules. So we're going to find that that will end up being insoluble. For a slightly polar molecule like acetone, which is actually fairly polar, we will find that it is capable of dissolving in a non-polar solvent like carbon tetrachloride, and that's because the acetone doesn't do hydrogen bonding itself, but it does interact enough with the carbon tetrachloride to make it dissolve. Again, you also get the entropy effect because when you mix the molecules, you disperse those molecules, and the more you disperse them, then the more ways there are to distribute the molecules, and therefore the higher the entropy. Second law of thermodynamics is the thing going on there. Okay. Acetone and water, there is a very strong interaction between the lone pair electrons on the acetone and the hydrogens on the water. So you do get a hydrogen bonding interaction there, which makes it quite soluble in water. That makes acetone really good for cleaning up things. It'll clean up things that are nonpolar, and it'll clean up things that are polar, right? Whereas if you just clean with water, then it's hard to get those nonpolar things without going to some other stuff, which we'll talk about here in just a second. All right, so hydrogen bonding, here is the picture. So hydrogen bonding makes acetone soluble in water. And again, these are completely miscible, which means that we can dissolve them in any ratio. So acetone has a lone pair of electrons on the oxygen. It's capable of accepting a hydrogen bond from water. Therefore, we're going to get good solubility. So, ta-da. All right, and yes, since there are only 3 carbons, that one polar functional group is enough to get the 3 carbons to dissolve. If we threw a couple extra carbons on either side there, it'd start to become insoluble. So we will find that the size of the molecules will matter for solubility purposes. So ethanol, and I'll just draw the pictures up here. Ethanol has a polar OH group, which interacts really, really well with water, but it only has 2 carbons. So that ratio is less than 1 to 5, or greater than, or yeah, it's less than 5 to 1 if we want to think about it that way. So and so because there are 2 carbons there, and we have that big OH, then it's quite soluble in water. So you can mix ethanol and water in any ratio, from 0% ethanol to 100% ethanol, and it will always form a solution. Cholesterol, on the other hand, it does have that polar OH group, but there's 27 other carbons out here, and so all of this stuff is nonpolar. The nonpolar part of the molecule, we refer to it or the polar part of the molecule, we refer to it as hydrophilic, and here's the word down there, hydrophilic. So OH is hydrophilic, but the rest is hydrophobic. So the rest of that is hydrophobic, and the hydrophobic part will make it so it doesn't dissolve. So if you take cholesterol and you put it into water, it will float on top like grease on water. All right, so wrapping up all the solubility things that we've talked about, ionic compounds, and it's definitely not all ionic compounds, but many of them, they'll be soluble in water and insoluble in nonpolar organic solvents like carbon tetrachloride or benzene. All right, let's see. For something that's completely nonpolar, it's typically going to be insoluble in water. There's just no interaction. The only thing you get there are the dispersion forces, and those just aren't strong enough to overcome the old interactions you had to give up. So insoluble in water, but it should be quite soluble because nonpolar should go together quite well. It should be quite soluble in carbon tetrachloride. All right, here, this one is propanol. This is related to like isopropyl alcohol, which is rubbing alcohol around your house. We've got that OH, which is it's hydrophilic. And then we've got less than 5 carbons there. And so with less than 5 carbons, that should be soluble. And we'll find that indeed this will mix in any ratio, 100% miscible with water. Whereas if you take that and put it with the carbon tetrachloride, you'll find that it is also soluble. So it is also soluble. However, if you go to a long alcohol chain, so let's say instead of just having 3 carbons here, you have 11 carbons, well, since there's more than 5 carbons, that's not going to be very soluble in water. It'll still be soluble in our nonpolar solvent, carbon tetrachloride, benzene, that kind of thing. But it's gonna be insoluble in water. This will be, again, it'll be like having oil on water if you try to do it. So let's look at number 33. 33 is pretty easy. We'll look at number 33 here. So rank the compounds in each group in order of increasing water solubility. So here, let's see, we've got a polar compound. So this is polar. So we have dipole-dipole interaction. Here we've got an oxygen, so this is a little bit polar, and this is going to give us a little bit of hydrogen bonding, so that's going to give us a little bit more than this one. And then here we've got something that's completely nonpolar, CH3, CH2, CH2, CH3. So that one should be the least soluble, and then this one has the OH, so it should be the most. So our least soluble is CH3, CH2, CH2, CH3. All right. Next is going to be just our polar one that's not capable of any hydrogen bonding. And so that'll be CH3, 3, C, Cl. And then we're going to get the ether here. So CH3, oxygen, CH2, CH3. And then finally, our most soluble one is going to be the alcohol. That one should be completely miscible. So CH3, CH2, CH2, OH. All right. In a similar fashion, we can go through these. The one that should be the most soluble is going to be the alcohol. And the one that's going to be the least soluble is going to be this one, that carbon-bromine bond. It is polar, so we'll get a little bit of solubility, but not very much. So we'll have that one will be the least soluble. This ketone, we do have the lone pairs there that are capable of hydrogen bonding, so it'll be a little bit more soluble, although I don't think it'll be completely soluble. I'd have to look that up. And then our most soluble one, as mentioned, is going to be that alcohol. Now, I wouldn't anticipate it would be 100% miscible with water, but it should at least have some solubility in water. All right, let's go back to our presentation. And we want to look at applications of solubility. The first application we're going to look at is vitamins. And so here up on the screen, we've got beta carotene and vitamin A. Beta carotene your body will convert it into vitamin A. That's one of the things that you do. So you eat foods that have beta carotene in them, and then your body will generate the vitamin A. But you'll notice here that this is all very nonpolar. So this whole thing is going to be very hydrophobic. There's no heteroatoms there, very little polarity involved in beta carotene. Vitamin A, well, most of it is hydrophobic, so all of this stuff is nonpolar, and it's just this little bit on the end that is hydrophilic. And so this is not going to be very soluble in water either. So we'll find that vitamin A typically shows up in oils, and as a consequence, that means that, well, when your body processes it is possible to get too much vitamin A. When your body processes it, it has to process it through the liver. If you get too much vitamin A, it can actually stress the liver, although I don't know if there's been any cases of vitamin A poisoning. It is something, if you have a liver disorder, you wouldn't want to have too much of the vitamin A. You want to get just the right amount. All right. Vitamin C, on the other hand, is very hydrophilic. It's got OH, it's got the carbonyl here, and a couple other OHs there. And all of those are capable of hydrogen bonding with water. And so vitamin C, or ascorbic acid, as we like to refer to it, is very soluble in water. That also means that when you consume it, if you get too much in your body, which it is possible to do, your body is capable of processing it and removing it from your body quite easily, removing it from your bloodstream and passing it into your urine. And so that is that's good. So it's very difficult to overdose on vitamin C, where it is possible to overdose on vitamin A. So I won't say it's impossible, because some people have allergies and stuff that. All right, here I'm going to admit something. I have an allergy to vitamin C at high doses. Of course, I have to have vitamin C in my diet, otherwise, otherwise bad things would happen. I would get scurvy, right? But if I get too much, I actually feel pretty miserable. I get hives and stuff. It's unpleasant. All right, enough about my personal imperfections. All right, another thing that I like to discuss when we talk about solubility is soap. And soap, thanks to our coronavirus pandemic, we're all aware of how important soap is and how much we have to wash our hands and wash stuff away. And so let's just talk real quickly about how soap works and what that means in terms of cleaning our hands and stuff. So soap has two components. There's a part up here. This is the conjugate base of a carboxylic acid, and so it's a sodium salt of a carboxylic acid. And this part is quite hydrophilic. That ionic interaction interacts quite well with water molecules, and so it is relatively easy to get some soap to dissolve in water. Now, this other part, we get this long chain, and that is very nonpolar, and that nonpolar part does not interact well with water, and but it does interact with other things like grease, oil, stuff like that. So if you've ever noticed, let's say you get some oil on your hands, like you're changing the oil on your car, or you worked with something, you got grease on your hands. If you just go to the sink and start rinsing it with water, you're not going to get it off very well. It's going to take a lot of work to get the oil off your hands. So what you do is you go to you go to your sink and you get a little bit of soap, and you also use warm water, because the warm water makes this work a little bit better. And when the soap interacts with the oil, it will, all those long tails will sort of insert themselves into the nonpolar interior, and it'll pick up little bits of oil, and you'll get little droplets of oil that are completely surrounded by the soap molecules. And then the soap on the edges interacts quite well with the water. And when we get this kind of structure, we call this a soap micelle. And so what happens is the little bit of oil or grease or whatever was on your hand gets turned into this micelle, and then it gets washed down the sink and biodegrades later, hopefully. But that's how that works. This happens faster and more efficiently if you use warm water. So wash your hands with warm water. Now, as far as bacteria and viruses, we'll find that many of the bacteria and viruses, that their proteins get denatured when soap comes in contact with them. The little tails kind of insert themselves down in there, and it can denature the proteins and disrupt the cell and cause it to die. Or if it's a virus, it can deactivate the virus. So, obviously, wash your hands with soap and wash them well, so you get your whole hands and everything. And then next time you're washing your hands, you have grease on your hands. Think about soap micelles. So the little micelles are surrounding the oil and rinsing that oil down the sink. It's kind of cool to think about. All right, and then yes, here this part is hydrophobic. I forgot to put that up. So, okay. When it comes to cell membranes, there is what's called the lipid bilayer at the surface of a cell. And that lipid bilayer has, well, as it's mentioned here, we've got this hydrophilic part, and then down here we've got this hydrophobic part. The hydrophobic part forms a bilayer, as the name suggests. And then the polar heads are at the surface, so they can interact with water. Here we can interact with water. But because of this, it's kind of a boundary to prevent just random stuff from getting from outside the cell to inside the cell. So we still want stuff to be able to do that, but we want to kind of be able to control it. And so there are all kinds of things like proteins and other stuff that will allow some transport to happen. But there are also molecules that can help transport across the lipid bilayer. So this is kind of a cool structure. It's kind of amazing that this just sort of happens. But anyway, there are things that are called ionophores, and the ionophores, they form complex cations with the with ionic compounds, so like sodium or potassium or whatever. So these can form these complex anions, complex cations rather. The cations will have an ion dipole interaction with these polar bits of the molecule. So they have a hydrophobic exterior, which is able to get through the lipid bilayer, and a polar interior, which allows for ion dipole interactions. All right. And then the ionophore can transport an ion across the cell membrane. So you have that ionophore, the ion can get in there and actually get transported across. I'm not sure what sort of sorcery is going on here, but hey, there you go. All right. There are things that are sort of synthetic ionophores, ones that, the one like synthesizing these would be kind of difficult. So we have some that we can synthesize that are easier to synthesize. And crown ethers are a category of these. This one's called 18 crown 6. And if you count around, you'll see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 atoms are in that ring. 6 of them are oxygens. And so that's where the 18 crown 6 comes from. And you'll see it's a regular pattern. So 2 carbons, 1 oxygen, 2 carbons, 1 oxygen. Well, it just so happens that we've got this polar interior with all these lone pair electrons that can interact quite well with a cation, not with an anion, but with a cation. And this one happens to be pretty selective to interact with potassium, so the K+ ion. All right, so the exterior of the molecule makes it soluble in nonpolar solvents, but the interior of the molecule is quite polar and interacts well with that ion, with an ion dipole interaction. Now, it just so happens that this size is very selective for potassium. If you do the 15 crown 5, where you have 1 fewer link here, so you have 1 fewer oxygen and 2 fewer carbons, you end up with one that is pretty selective for sodium. And if you go down to 12 crown 4, you have one that's pretty selective for lithium, which is pretty cool. Now, these will also interact with other ions, so it's not limited to our group 1, but it is kind of cool that a relatively simple to synthesize molecule, you can do this. So it's very, very useful to take this to make ionic compounds soluble in nonpolar solvents like benzene. That's a big deal. All right. Functional groups and reactivity. So we want to look at this last little bit here. So functional groups contain a heteroatom and a pi bond or both. If it doesn't contain either of those, then it is an alkane and doesn't have much interesting functionality to it. But these different types of structures, either the heteroatom or the pi bond, will create electrophilic, which means electron poor. It loves electrons, so it's seeking out electrons. So electrophilic sites and nucleophilic sites. And the nucleophilic sites are electron rich, and they want to seek out a positive charge. Typically, an electronegative heteroatom makes a carbon atom's electron poor electrophilic. And so here is an example. This is an alkyl halide. So we have 1, 2, 3, 4, 5 carbons. So this is 1 chloropentane. Well, that carbon-chlorine bond is polar, and the carbon has a partial positive charge. The chlorine has a partial negative charge. And so this partial positive charge makes that carbon electrophilic. Same thing with this one, although there's a lot of other stuff going on. The oxygens can be nucleophilic, and then the hydrogens can act like an acid. So there's other stuff going on this one. But this one, pretty much, if you've got a nucleophile, it can come in and react with that electrophile. When we're looking for nucleophilic sites in molecules, we're looking for either lone pairs. All right, so here we've got an ether and an amine. And so the lone pairs on there could potentially act like nucleophilic sites. They can also act like basic sites. A little bit later in the semester, we're going to talk about what makes something a good nucleophile versus what makes something a good base. And sometimes they're the same thing and sometimes they're not, but we'll get to that. Pi bonds also create these nucleophilic sites and are much more easily broken than these sigma bonds. And so alkenes, alkynes, those are a couple of examples of things that can act like nucleophiles. So when we're analyzing the reaction of pi bonds with electrophiles, then the electrophile comes along and reacts with the pair of electrons that is in that pi bond. So if I've got an alkene, then the electrophile can come along and react with that. And so the alkene has the electron rich, and then this electron poor thing comes along and reacts with it. All right, and then reactions of nucleophiles with electrophiles. If we have an electron poor, like a carbon, here, this carbon is electron poor, and then we have something that's electron rich, like this nucleophile, it can come in and react with that. We're going to talk about what makes something a good nucleophile in a later chapter. So let's look at number 56 on the in-class assignment, and here we're just trying to label things. We're trying to label the electrophilic and the nucleophilic. And oh, by the way, before I switch over, that's the last page in chapter 3. So, all right. So here we go. We want to label the electrophilic sites and the nucleophilic sites in each molecule. All right, so really the thing to do here is to identify where the partial charges are. So this is a polar bond, so we're going to have a partial positive on the carbon and a partial negative on the iodine. Well, that partial positive, that is electrophilic. It's positive, so it's seeking out electrons, so that is electrophilic. And this iodine should be a little bit nucleophilic, although it's not going to be a great nucleophile in that particular case, but we'll say that is nucleophilic. All right, here we'll have a partial positive my little deltas there are kind of sad. Let's try that again. All right, that looks a little bit better. And then a partial positive on those carbons and a partial negative on the oxygen. Well, those partial positives are going to be electrophilic, although I will say they're not very good electrophiles. And then this oxygen here, right, that's going to be nucleophilic. On this, we don't really have any polar bonds, and so we do have the electron-rich ring here and the electron-rich alkene there. And so I'm just going to point to that and to the aromatic ring, and that these are potential nucleophiles. We don't really have any electrophile action going on here, and that's simply because there's no polar bonds there. So we don't really get a partial positive anywhere. This one, we definitely get a partial positive. We get a partial positive on that carbon, a partial negative on the oxygen, and a partial negative on that carbon, or on that chlorine. That partial positive is going to be a very electrophilic site. So that will be electrophilic. That chlorine's not very good at being a nucleophile, either is that oxygen. We'll go ahead and label it as, I'm going to put it in quotes, nucleophilic. When we get to later chapters, and you'll see that I say it's nucleophilic, but man, it's not very. So that's why I'm putting it in quotes there. All right, well, that is the end of chapter 3. So look for chapter 4 soon. And that's the end of that chapter. All right.